Did you come up with a way of engineering this shortcut a little bit? Did you come up with a shortcut that you think still could be equally effective to the one we used on page 7 that saves us from having to do all of these derivatives and integrals? Because if so, you probably noticed something that was not just a coincidence and hopefully allowed you to think about the shortcut in relevant terms. The thing that we want to remember about the fundamental theorem is this, that when you take a derivative of an integral, those two operations should cancel each other out. That should happen, that will happen, that is just algebra. That has to happen. They're two opposite operations. The thing that we had to remember always about when that cancellation happens is that the dummy variable gets affected. In that cancellation process, the x squared needs to become part of the actual function, not part of the thing that cancels out. The x squared needs to become part of the actual cos function. So if we're going through the motions of things, we should expect that the derivative and the integral cancel each other out, leaving us with just the cos function, and in the cos function, the x squared. But if I write that, that doesn't look like the answer that I got when I did it the long way. Something's missing. So this is where we have to now let our shortcut evolve a little bit. If the thing inside our new function, if the thing that replaces the dummy variable, the x quantity, is not just x, it's x squared or anything that would necessitate a chain rule, anything that would necessitate a second step, we have to multiply by its derivative. Did you notice that the 2x that we got in the front was simply the derivative of the inner function? When we did the long work, when we actually did the whole process, that 2x was the derivative of x squared. That 2x was just part of our chain rule. So that 2x needs to be part of my answer because the derivative part of my answer required a chain rule. But let's see if we can make sense of it. Whether we put it at the front or at the back of the answer, it doesn't matter. I can just as easily write my answer like this. We still could make this work with my shortcut. Let's just make sure that we think about the logic here. The logic still for the fundamental theorem is cancel the derivative and the integral, take whatever's left, the original function, replace the dummy variable with whatever your unknown limit was, x squared, and then, if needed, multiply by the chain rule part, multiply by the derivative of whatever that new variable is. Now, that doesn't seem quite as easy as the previous questions. So it probably does make you wonder, why weren't we doing this on page 7? Why wasn't this part of the previous lesson? Why now do I have this extra step to think about, where I cancel and multiply by an extra derivative? Why now? Technically, if you think about that, I actually have been doing this all along. I'm going to go back to page 7 where we did some examples. I want to illustrate something here. Technically, we've been doing this process the exact same way the whole time. We just didn't have to think about it this way. Notice, in number 3, letter A, it's one of these problems. The derivative and the integral cancel each other out. I have the square root then of, instead of t squared minus 1, I'm plugging in the upper limit, so x squared minus 1, times, chain rule, the derivative of what I'm plugging in. Oh, well, the derivative of what I'm plugging in is the derivative of x, 1. So, yeah, the answer that I got in the previous lesson is the same thing. I just didn't have to think yesterday about the chain rule because I wasn't doing problems that required what I thought to be a chain rule. It is a chain rule technically, I just wasn't thinking in those terms because the chain rule is not very obvious when the inner function's just an x. But that mathematically is what's going on. That mathematically is what's happening with the fundamental theorem of calculus. So specifically, this is where I want to make sure that we evolve the fundamental theorem to something that really has a distinctive set of steps, something where you know, like, this is what you need to do. In that space above question number 3. So I'm back on page 7, and I'm looking at where the second fundamental theorem of calculus is written, it's still all abstract and funky, and I don't think that's very helpful. So I'm going to fold a bit of my paper up and make a translation into real steps that I think that will help, and that I think will sort of summarize this effect of the chain rule now. Here's what this really means. When you have a second fundamental theorem problem, here are the steps to follow. And I'm going to write the steps as clearly as I can, but I'm also going to write an example, so that way you have something you can look at, something that you can say to yourself, oh, okay, like I get what those steps mean. Here's an example of what those steps look like. So let's just consider for a second one of these problems. I'll just make one up. d dx of, so the derivative of, and let's do an integral. We'll do the integral from 5, I'm just making this up, to, let's say, 3x to the power of 4. Just going crazy. And then I'll just make up a random function. T times, let's go crazy, t times e to the t dt. So we'll just throw lots of stuff in this example, just so that way it looks crazy and we can make sense of things, knowing that this is going to be a good template for all sorts of possible situations. Okay, so I don't want to do this as a real derivative. This looks like or a real antiderivative either. This looks awful. I have a product rule. It's definitely hard to do product rules. I have to do some sort of u sub. Even the u sub here might be a little messy. Let's not even bother with that nonsense. Let's apply our fundamental theorem. What's the point of having a shortcut if we don't use it? Let's use it. Derivative of an integral. Those two things are going to cancel out. So first step is to cancel the derivative and the integral. Now when you cancel the derivative and the integral, so notice I'm abbreviating my writing here, and you might want to make sure that you write it in more fully fleshed out words, just in case that shorthand doesn't really make sense to you. These are your notes after all. Make them helpful. So if you're looking at this and saying, okay, cancel the derivative and the integral, you can also make a note to yourself, and the dt. That technically cancels as well, because it's part of the integral. dt and the integral are attached, so when the derivative cancels the integral symbol, the dt goes as well. So when you cancel, what you're left with should be the original function. So take your original function, I'll say you can write your original function, but plug in the upper limit. The upper limit should be the one with the x. So when I look now at the original function, the part that should be left over when my derivative and integral canceled each other out, I need to plug in that upper limit. So I'll just highlight so you can see what I'm plugging in here. That 3x to the 4th needs to be plugged into my dummy variable. Now there are actually two dummy variables that I need to plug into, so I need to plug in both of them. Since both of them are dummies, both of them need to be replaced. So I'm going to write it out. I have something e to the something. And I like to use parentheses when I write this out. You don't have to. It's up to you. I just like parentheses because that reminds my brain I need to plug something in. And I'm going to plug the upper limit into those parentheses. So 3x to the 4th plugs in. 3x to the 4th plugs in. Fantastic. But then I remember, oh crap, hold on. I was doing a derivative. I still have to account for the chain rule. 3x to the 4th does have its own derivative, so I technically still have to multiply. So this is my third and final step. Multiply by the derivative of the upper limit. That's my chain rule step, because that's technically my inner function. The upper limit is my original function. So I still have to multiply by the derivative of that thing. But that's just an easy little derivative. That's no big deal. Bring down the 4, so that's 12x cubed. Now this technically is my answer. If it's bothering you because you're like, oh, clean that up, Herbert, that's an awful looking answer, you can totally clean it up if you want to. That's an optional step. It's just like the chain rule. You can clean things up. It's not like you have to. But if you wanted to, 12 times 3 would be 36. Then I have x to the 4th and x cubed, which is x to the 7th. And then I have my e to the 3x to the 4th. And that is my answer. Now, that is a crazy looking answer. I can only assume that if I really did this with proper calculus, like if I really did the antiderivative, and then did the derivative with the chain rule, it would have been messy. So, the fundamental theorem, while a little hard to keep straight, definitely gave me a much easier way of processing this information. I canceled the derivative and the integral. I wrote out whatever was left. I just left parentheses where the dummy variables were. I plugged in those dummy variables as 3x to the 4th, and then multiplied by the derivative of 3x to the 4th to do the chain rule. So the moral of the story is, yes, these problems do involve chain rules, because they're derivative problems. Technically, that's why they're chain rules. These are derivative problems. They have integrals in them, but the fundamental theorem, at its core, is still a derivative problem. So that's why the chain rule has made its ugly return. We are doing a chain rule because we are technically doing a derivative. Every derivative is actually a chain rule. Just like we saw on page 7, though, sometimes you're multiplying by 1, so it doesn't seem like it, but every derivative is a chain rule. Now, let's make sure that we summarize everything that we've seen in a few examples so that we can start to apply this process, so that we can start to make sense of things. The next video is going to walk you through some examples of applying this chain rule on page 9. So take some time to do the following steps before you begin that next video. First, make sense of what we just wrote. These notes that we just broke down, make sure every step made sense. Why did we do each of these things? What did it look like in the context of an example? Why did the answer look the way it did? Make sure that makes sense first. Second thing to do before the next video is to finish page 8. Remember at the bottom of page 8, we didn't actually finish the question. In letter E, that was the open question I had posed to you. Is there an easy way that you can condense the process? That's what these notes attempted to answer for us. Yes, there is an easy way. Here's how to do it. So take some time to go back to page 8 and try to do the original problem with the shortcut approach. Try to ignore everything that we did the long way and try to go directly from this original problem straight to the shortcut process using the steps that we just derived. If it works out, you'll get the same answer that we did by doing it the long way. But this will be a great opportunity for you to practice for yourself. Does it really work? Does the shortcut work just as well as the long way to do it? Because if so, it'll really reinforce to you that that shortcut is worth knowing, worth understanding. So again, 2 tasks. Make sense of the steps, make sure that you're good there, and then apply the steps to this example in number 5 to make sure that it makes sense in the context of an answer you're already expecting to see. You will apply this. You will get 2x cos x squared. It will work. I know it because we've already done it the long way. We already know what the answer is supposed to be. So make sure the steps work for this process so that you can use them effectively on page 9. On page 9, we'll be getting into a series of practice problems where having a couple good examples will be very crucial. That's why it's so important to take the time to understand the steps and finish page 8 so that those steps will make sense when we need to use them.